One of the drawbacks of stochastic gradient descent is that you have to set the learning rate yourself, which is an extra hyperparameter to tune. In today's video, I will present adaptive gradient algorithm, Adagrad, which is a modification of stochastic gradient descent, which doesn't really require you to tune the learning rate yourself, and that work really well in setting where data is sparse. The main idea of Adagrad is to keep in memory the sum of squared gradient up to a certain point. This matrix that we will be creating will serve as a scaling factor that will dampen the extreme parameter and prioritize the learning of parameters that get few or very small updates. So the full formula looks like this. It's very similar to stochastic gradient descent. So let's break it down. So first off, we have theta at time t at I. So this is the current parameter value at I at the current time. So theta t plus 1 at I is the updated parameter after one time step. And over here is our learning rate, which is set to 0.01 usually. So there is no real tweaking of the hyperparameter needed. Epsilon over here is only there to avoid a division by 0, and usually it's like 1 to the e minus 8. So gt at I is the current gradient that we calculated, just like in the stochastic gradient descent. And finally, big gt at II is the core of the Adagrad algorithm. So let's take a deeper look into it. So G is defined as the cumulative sum over all previous time step of the gradient of the square gradient. So what is really interesting for us, if you look back over here, is the diagonal at II. So this is really what we're looking at. Here we have a summation from the time equal at 1 until the current time, and what we're summing up is gradient exponent 2 at given j. Here j represents the position of the parameter that we're updating. So parameter 0 will have a j of equals 0, and so on and so forth. Here it's as if we had only the diagonal matrix, so why even bother with this? Why not use a vector? Because over here you see you have a multiplication, but it's a vector with a matrix. We could do here a vectorized implementation of this, which will use a dot product, which can be way faster than doing it iteratively. So this is why we have diagonal matrix, but treat it as a vector in your head. So basically what we're having here is a running sum from the start of the learning until the current time. So this means that if we have a large gradient, only a small amount of learning will happen because the bottom part will be huge. So we're going to divide the learning rate by a lot. Furthermore, if the feature isn't frequently there, so if the feature space is sparse, the update of the parameter will be bigger since it's a cumulative sum. So if we have something that is always happening, it will accumulate and the bottom part will be bigger, so the learning rate will go down. However, if we have a lot of zeros and at some point we have a small value, this is where the learning rate will be bigger. So this is why this algorithm is great for text and image learning, as it tends to have a sparse feature set. So like here we have some feature space of a text classification, and the feature space, you see there's a lot of zeros and 1, but there's way more zeros than 1. So let's now look at an implementation of the algorithm in Python. Okay, so we're in the notebook. The notebook is on the GitHub, linked in the description. So we're just going to do a super dumb setup where we have like a small feature space. So here we have this linear function that we're trying to learn. So we have the bias and the slope. Adagrad is not really made for this, but it was just to test it out. So this is what we're going to do. We're gonna have some gradient that we're gonna hardcore over here. If you were to do it in a neural network, you will use something like the compute graph, but here we keep it simple. So this is my function, this is this partial derivative for the bias, and the partial derivative for the slope. And this is what really matters. And over here we're testing it out with some simple setup. So here we have intercept of 0 and slope of 1, and try to learn this from the data. Try to learn the W0 and W1. So if we look at the algorithm per se, we have the x's, the y's, we have this learning rate, which is shouldn't move from 0.01 because that's the whole point of Adagrad, and then the number of iteration and the epsilon over here. So this is really the setup you will see is really similar to stochastic gradient descent. It's just the G matrix that will change. So here we initialize W0 and W1 randomly. Here we're creating our matrix, and if you see we have a 2 by 2 because we just have two elements. Over here this is the main iteration loop, really simple stuff. So what we're doing the stochastic part where we're permuting and then we're taking a random sample. Then we just take that random sample over here, and over here this is where we calculate our gradient by feeding into this function. So those are pretty simple. We just calculate the gradient by hand by doing the partial derivative. Here this is the important part where we update the diagonal of the matrix. So we update it by doing the gradient times the gradient, and then summing it up. So we're doing a running sum like this. And over here this is the important part. This is where the update is taking part. So remember we have W, and then we have the learning rate divided by something, and this something in the square root of the j at ii plus the epsilon, and time the j over here for this whole thing. So that's pretty much that. There's nothing fancy, it's just that this is something that works well with sparse matrix. So let's look at if this thing is actually working. So can we get down to, he's having trouble with this one. Yeah. This one will run for a while. Like I said, it was not made, the Adagrad algorithm is not really made for this, and you see it's going down, but it needs way more iteration. In this case, choosing a smaller learning rate like this will actually, I'm pretty sure, will help. Yeah, it's helping a lot. So yeah, I think I'm gonna leave it at 0.1, but the whole idea of Adagrad is that you don't have to play with this, but the 0.01 learning rate is for text and sparse feature space. Let's look at how we behave with intercept at 0 and slope at 2. And can it go down? If you see over here, it started to go up and then it went down. For the W0, went down again. Yeah, we're getting close to that, so it's actually not too bad. So it's able to learn the stuff. Let's look at intercept 1 and slope of 2. So this is the random initialization, and then yeah, it's converging to this. So it's working. So the algorithm is working. So you have to take into consideration that you don't have to tweak the learning rate. So you may need more iteration, but it will be able to get there. There are some limitations with Adagrad. For instance, because you're doing a sum, at some point you're going to divide by something that is big, so you will not learn anything. But here this is not the problem. The problem is the learning rate is not well suited for this type of function. So that's it. So that was the Adagrad algorithm. I hope you learned something today. If you have comments or questions, you can leave them in the comment section. Have a good week.